Let's get started on taking a look at Albert Einstein's theory of special relativity. Now, the origins of the theory of special relativity are really found in the laws of Isaac Newton and Galileo and all of these other physicists that we've been studying prior to 1900. But what was different about what Einstein did compared to what all of these other scientists did was Einstein was able to pare down the necessary ideas in physics and say, these are the ideas in physics that we have to verify and that have to apply in all situations. And sometimes those ideas that he pared away were quite surprising. One of them was from the result of the Michelson-Morley experiment. The Michelson-Morley experiment indicated that the speed of light was constant in all situations, and this was against what seemed to be the ideas of Newton and Galileo. For instance, if you are running forward and throwing a ball, then that ball will move faster than if you just stood still and threw that ball. But if you are carrying a flashlight, and you are running forward carrying that flashlight, and you turn the light on the flashlight on, the light leaves that at exactly the same speed as if you were just standing still. And so that just seemed really weird at the time. But on the other hand, maybe it's not so weird, because if light reached us faster from objects that were approaching us, then we would start seeing some strange events. For instance, let's suppose that we have a stationary observer and two other observers, and there is this dramatic effort to avoid an accident. Now, what would the stationary observer see, considering that the one car is directly approaching the stationary observer? And in Newtonian or Galilean physics, light from that car approaching the observer would be moving faster. If it was moving faster, then the stationary observer would see that approaching car trying to swerve and avoid nothing, because light from the red car reaches the stationary observer before light from the other car. And yet we see these things happen instantaneously. So the light coming off of a moving source, it's already kind of built into our ideas, into our everyday experience, that it has to be traveling at the same speed. So Einstein thought about that, and he decided that we needed to make sure that the laws of physics were the same for all observers in the universe. Not necessarily the same observations, but the laws of physics. If you build up all of these observations to generate the laws of physics, everybody in the universe should be able to agree on the same laws. Einstein realized that this was going to involve some really complicated math, and so he decided to do an initial approach that is called special relativity. In special relativity, the assumption is that all observers are moving at a constant velocity with respect to each other. So Einstein figured if he could come up with a theory for that basic situation, that could serve as a foundation for incorporating other situations, and he ultimately did that in his theory of general relativity. But frankly, the math in general relativity is horrifying, and we're not going to touch it. Special relativity, on the other hand, it's basically algebra, and the math is a lot simpler than the aura of the theory might indicate. That the theory just sounds really complicated and stuff like that, but the math is surprisingly not that bad. So what Einstein did was, he said the laws of physics have to be the same. And one of those laws would be that the speed of light was constant throughout the universe. He didn't prove it. He just said it was a property of the universe. So it was his end run around the problem. he didn't explain why the speed of light is constant. He just said, it is constant. What are the consequences? So we have a lot of respect for that because people got bogged down in trying to figure out why the speed of light was constant. Einstein was like, it is constant. Let's see what happens. So when he started thinking about this and putting some effort into it, he came up with a couple of surprising results. Keep in mind that when observers are moving with respect to each other, they're not necessarily going to agree on the same observations. It's just, as we said before, they ultimately have to build up to the same laws of physics. But disagreement on these observations led to disagreements on things that no one would have thought there would be disagreements. For instance, the length of an object. How long is a meter stick? Well, it's a meter long, isn't it? Well, not if you're in motion with respect to that meter stick. Because when you look at a meter stick, you see, let's say you're holding it with one hand close to you and the other end extending away from you. When you look at that meter stick, you see all of it at once. But the fact of the matter is, light at the far end of the meter stick left just a little bit earlier to reach you than light at the near end of the meter stick. So that discrepancy in the timing of the emission of light, normally that doesn't have any impact for us. But suppose our speed or the speed of the stick relative to us is close to the speed of light. If that starts happening, we get a significant effect. Rather cheesy animation on the screen, but if you consider the observer standing on the stick and moving with the stick, the observer on the moving stick is going to see it longer than the observer who is standing stationary. Now, the observer moving with the stick is in the same frame of reference as the stick. They both have the same speed. We say they're in the same frame of reference. The person with the stick in the same frame of reference as the stick sees it longer than the person who is not in the same frame of reference as the stick. It can also apply kind of in the other situation. Suppose the stick and the person are stationary and the other person is in motion. Well, the other person in motion relative to the stick is still going to say it's shorter than the person who is moving with the stick would say. If you are in motion with respect to this stick, you are going to say that it is shorter than a person who is holding the stick would say. Now let's apply this idea of length contraction to the following situation. Let's say you're driving your car slightly in excess of the speed limit. Let's say you're driving it at half the speed of light, and you're driving it from Harrisonburg to Richmond. Now, if you compare the path that you take with the path taken by another person, following the same roads, but would you say that the distance from Harrisonburg to Richmond is the same as someone driving at 65 miles per hour? Is it longer or is it shorter than someone driving on the road at 65 miles per hour? Along with length contraction, there is time dilation. What is time dilation? Time dilation is the idea that's really been grabbed onto by science fiction enthusiasts. It allows for the possibility that if you travel really fast, then you can visit distant parts of the galaxy without having centuries, thousands of years, whatever of your life go by. In principle, if you are traveling fast enough, you can cross from one side of the galaxy to the other side of the galaxy in a span of, from your perspective, just a few days. Now, let's try and understand time dilation, and it does involve the fact that light travels at the same speed no matter what your perspective is. There's a link to kind of a simulation of a famous experiment, a thought experiment that Einstein came up with. And what we have are two individuals, not very wittily named Jack and Jill. Now, I can run this simulation, and both Jack and Jill emit a pulse of light that travels to a mirror above them, reflects off the mirror, and returns to them. So let's just run this. So you see the pulse of light, it's traveling up, it reaches the mirror, and it reflects back, and when it arrives at Jill, and for that matter Jack, the simulation stops. And you can see that both of them say that 8 seconds have gone by. But now, let's give Jill some speed. So let's reset things. Let's give Jill, let's say she's moving at half the speed of light. So Jill is going to be moving to the right, and along with her moving to the right will also be the mirror above her. Jack will stay stationary. So let's watch what happens. And the pulse of light travels at the same speed, but now in the case of Jill, it has to travel a longer distance because it's traveling at an angle. And so the pulse from Jack is going to return to Jack first, and then finally it gets to Jill. Now, Jill will say, well, that took only 8 seconds. Jack might say, but it looked like that it took 9.22 seconds for you. So Jack is saying his own pulse was 8 seconds. But the event in question is, how is it going for Jill? Jack is stationary along with you and me. And our clock and Jack's clock say 9.22 seconds elapsed. Jill says, nope, it was only 8 seconds. As far as Jill is concerned, the light pulse traveled up, it struck the mirror, and it returned back to Jill. Let's give Jill a pretty significant velocity. Let's say she's at 90% of the speed of light. Now, this is going to take a few seconds because these pulses in the simulation are not traveling very rapidly. But they're both traveling at the same speed. It's just now Jill's pulse has to travel a pretty long distance before it can reflect. And it looks like Jill might even be off the screen by the time that pulse reaches her. Nevertheless, I assume that the timer will keep going. And we see Jill said 8 seconds went by. After all, it takes only 8 seconds to go from Jill to the mirror and back to Jill. But Jack is saying that Jill has really slowed down. Jack is saying this is 18.3 seconds. Jill's clock is running really slowly. We look at Jill's clock and think, boy, that's slow. What is going on there? Jill is experiencing time dilation from our perspective. So, kind of weird that we would experience elapsed time differently. We have to be very careful in how we apply our equations for length contraction and time dilation. And this is where relativity can get a little tricky. The equations themselves are not really that horrible. You need to know what the speed is between both the stationary observer and the moving observer, and we'll call that V. I think length contraction is a little bit more straightforward. L naught is the length of the object in its own reference frame, the plank, the stick, whatever. And L prime is the length as measured by some other observer. So we imagine the plank is at rest in its own frame of reference, and it sees an observer whiz past it. So this observer is in motion with respect to the plank, and the observer will see the plank as shorter than the plank appears to be itself. So if we're talking about a meter stick, an observer in motion with respect to the meter stick will say it's shorter than a meter. L prime is the length of the object as seen by an observer in motion relative to the object. L naught is the length of the object as seen by an observer not moving with respect to the object. So this observer is in the same frame of reference as the object. A moving observer will always see it as shorter than an observer in the same frame of reference as the object. Always. The time dilation equation is a little bit trickier because you have to have a very good understanding of the event that is being timed. We saw Jack and Jill, and it looked like we saw two different events. One event was the pulse of light for Jack, and the other was the pulse of light for Jill. Which event do you pick? Well, that depends upon the context. In the simulation, we were picking Jill's event and looking at things from the motionless Jack's perspective. Be very careful with time dilation. T naught is the duration of the event if you are in the same frame of reference as the event. So in the case of Jill is in the same frame of reference as the event because the event is the timing for Jill. And Jill says 8 seconds. Jack, who is in a different frame of reference, is going to say, well, this takes longer. If you are in the frame of reference of the event, then you will measure it with the shortest duration compared to anybody in the universe. Anybody in motion with respect to the event is going to say the duration is longer than you do. Okay, that's probably confusing. Let's, first of all, simplify the appearance of our equations. We have seen V over C quite a few times, and this appears a lot in relativity. The speed of the object divided by the speed of light. And it's given its own symbol, the lowercase Greek letter beta. Another thing we see extremely frequently is 1 over the square root of 1 minus v squared over c squared, which is equal to 1 over the square root of 1 minus beta squared. Because that is seen so frequently, that is given its own symbol, the lowercase Greek letter gamma. Both beta and gamma are unitless quantities. The weird thing about length contraction and time dilation is, given a problem, you should be able to solve the problem using the length contraction formula and get a result. You should solve the problem using the time dilation formula and get a result. And those two results should agree with each other. But it involves some weird thinking. Let's take a look at an example. There is a subatomic particle that is called the K-long meson. And it has a half-life. It has a lifetime scale. It lives only for a short period of time. 50% of the time it's going to live only no more than 5.2 times 10 to the negative 8 seconds, 52 nanoseconds. So let's assume that we have one of these particles that lives 52 nanoseconds. And it's moving. And being a subatomic particle, it can move at a very high speed. Let's say it's moving at 95% the speed of light. And so we see the subatomic particle moving at 95% the speed of light, and we ask how far will it travel in one half-life after 5.2 times 10 to the negative 8 seconds. Well, let's first of all determine beta and gamma. Beta is V over C, V is 0.95C, 0.95C divided by C, the C's cancel out, beta is 0.95. Gamma is 1 over the square root of 1 minus theta squared, so we would do 1 minus 0.95 squared. We take the square root, then we would do 1 over that. And we get gamma equals 3.203. Pro tip here, beta is never greater than 1, and gamma is never less than 1. You should always find beta never more than 1. You should always find gamma greater than 1. If you don't find that, double check your math. So, time dilation demands that the half-life that is measured is different from 5.2 times 10 to the negative 8 seconds. That 5.2 times 10 to the negative 8 seconds is in the K-long meson's own frame of reference. Anything in its own frame of reference says it's motionless, and the rest of the universe might be in motion around it. So in its own frame of reference, the K-long meson says, 5.2 times 10 to the negative 8 seconds, time to die. But in the lab, where we see this particle whizzing past us, the clock for that particle is running slow as we see it. We see more time go by. In fact, we would see 1.67 times 10 to the negative 7 seconds, or about 167 nanoseconds. So that's how we would measure the half-life of this fast-moving particle. And if it's lasting for 1.67 times 10 to the negative 7 seconds and traveling at a speed of 0.95 c, well, the distance it travels is speed times time. We would measure it as 47.4 meters. We measure this distance it travels as the speed that we observe times the duration that we observe, 47.4 meters. Now, we can also use the length contraction formula. How is the length contraction formula going to work? The K-long meson in its own frame of reference says it is motionless, and it is the lab in which this experiment is taking place that's moving. So as far as the K-long meson is concerned, it moves 0 meters, but the lab is moving at a speed of 0.95 c. The K-long meson says, well, this is only 52 nanoseconds, 5.2 times 10 to the negative 8 seconds, and the speed of the lab is 0.95 c. The lab, according to the K-long meson, travels a distance of 14.81 meters. But that distance of 14.81 meters is this moving distance. In the lab's frame of reference, this becomes 47.4 meters. So we seem to have flipped around what the stationary frame of reference is, what the moving frame of reference is. This is where you have to be very careful in relativity. So in the case of time dilation, the event is the lifetime of the meson. And so we would treat the meson as the stationary observer, and the lab is moving with respect to the K-long meson. In the case of the length contraction situation, the question that is being asked is how far does it move? Implicitly, how far does it move as we measure it? We are in the lab. So what is this distance in the lab's frame of reference? So that becomes the rest frame of reference. So it's weird. You have to be really careful. This is the logical flow that you have to follow in order to get your results to agree if you're using length contraction or time dilation. What's the best approach? Try and do the problem both ways. Try and do the problem using time dilation. Try and do the problem using length contraction. See if you can understand what frame of reference should be the rest frame and get the same answer like we circumstances are. Now let's apply this to a situation. You're driving your car to Richmond, and again, you're moving at half the speed of light. And now, even worse, while you're driving, you're talking on your phone. Which, stop doing that. You shouldn't be doing that. But here you are, you're doing it. And so you're driving at the speed of 0.5 C, or are you? According to your frame of reference, you're stationary, and the road from Harrisonburg to Richmond is moving with respect to you at half the speed of light. Weird. In relativity, anything can be at rest. So even it gets a little nonsensical. So it says you're driving on the road to Richmond. Nope, you're stationary. The road is in motion with respect to you. Under these circumstances, as you speak with your friend over the phone, why is it difficult to understand them? Is it because you think that for your friend time moves slowly, so they sound like they're speaking very slowly? Or do you think that time is moving rapidly for them, so that they're speaking very rapidly? Is there an issue that makes the cell phone signal travel slowly? Or is there an issue that makes the cell phone signal travel rapidly? Which of these do you think is the answer? And as usual, feel free to ask questions at the start of class. Maybe you're feeling like this right now. Don't feel bad. It's confusing. I get it. We'll work through it. Take care. Bye-bye.